recording. We are recording. We're rolling. All right. So we're going to talk about series circuits. As I said, this originally was a slideshow by Stephen L. Herman, who is an icon in the field. And once again, he used the Ohm's law circle with 95,000 formulas on it, which you cannot possibly remember. But what can you remember? Pioneer wheels, right? Pioneer wheels. Okay, so if we work these with pioneer wheels and the two formulas we can derive from that. Let me go over that one more time. When we get to the first example, remind me, if I haven't done it by then, to derive the two formulas one more time. It's nice and easy, but let's do that next. Okay. Protective devices like fuses and circuit breakers are always connected in series. To understand that, I want you to notice, though, that this lamp 1, lamp 2, lamp 3, and lamp 4 are all wired in parallel because they have 4 different paths for current to flow. Let me see if this is going to work. Oh, it did. It picked right up. If this switch were closed, current could flow through here. That would be current path number 1. Everybody agrees with that, I'm sure. That should have been black because the first phase is always black, then it's red. But we're going to make it different this time. So we would have another path for current to flow. That's 2 of them. Uh-oh. What did I do? I don't think that's going to do it. All right, now let's go one more path, and we see that we have a path. If this switch were closed, we'd have another path here, and we'd finally have one last path over here. That's parallel because we have 4 paths for the current to flow. But notice that they all must go through this point or this point. All 4 of those paths are only one path at that point. Somehow I keep doing that. At this point in this line, this one single wire, and this one single wire going out where it's joined right here, it's one path. So this fuse, in spite of the fact that it's a parallel circuit beyond that, is in a series branch. It's series. Everything has to go through that one path to get out, right? And it's going to come back into this. Well, this is showing a grounded, but that's not really, well, thanks, Stephen. That's not exactly what we want to show them. It's not going to ground. It's going back to the neutral conductor, which is grounded, but that doesn't make it a grounding conductor. But that's a whole different opening. All right, so fuse, circuit breaker, that's got to be in series, and a series circuit is when we have one and one only path. Let's see, when determining values of series circuits, there are 3 basic rules which use with Ohm's law that will aid in calculating values of voltage, current, resistance, and power in any circuit with one power source. The rules are, we've gone over this before, but we're going to do it again. Voltage is additive. That's that first rule. Sum of voltage drops is the voltage drop across each resistor added together, right? So voltage drops are additive, which gives you the total voltage supply. So all the voltage drops have to equal the voltage supply. Can you have any voltage coming back? No, nothing is coming back. Whatever. So if we go back, let me go back to this slide before. If we look at this, in any one of these points, what is the voltage right here? Anybody? That voltage is 0. That is voltage 0. And let me show you why. Up here we have, let's say, 120 volts AC, theoretically, going in here. But the loads are dropping all the voltage across each of them. So there's no voltage coming back. If we measure from neutral point to this neutral point over here, what is the voltage potential difference? 0. That's right. Now what if we measure from this neutral point here to this Neutral point over here. What is the potential difference? They're the same potential. 0. Very good. Okay, let's move on. Okay. The current's constant. Wherever you look in a current series circuit, current is constant. And that makes it our most important series rule. It's rule number 1, in my opinion, not number 2. The total resistance is additive. In other words, the resistance across all the resistors creates a total resistance. First rule concerning series circuit is the current is the same at any point in the circuit. I wonder who wrote that. Once known, the amount of current flow through all the elements is known. The letter I stands for the intensity of current flow. I've said that a couple times. I'd like you to remember that. In this formula, I at any one, I total is equal to current through any single part. And I in is any number of them. Okay, resistance adds. Resistance is additive. Not a big deal. We've gone over that. Voltage drops add. And I like this drawing. It shows if you had a voltage indicator, sometimes known as a voltmeter, across resistor 1, resistor 2, and resistor 3, it would measure the potential difference change, which is the voltage drop. Very important. That is the voltage drop. And that will tell us our total voltage drops is going to be the voltage supplied, because the voltage supplied is going to be dropped across all the loads. So therefore, if we have no resistance, how much voltage will flow? All of it. If there's no resistance, how much current will flow? Well, 0 resistance. We can't divide by 0, can we? What's P-E-I-R? If we have 0 or 0.00000000001 divided by the voltage, it's going to be a very high current flow. Everybody see that? Remember that? Inverse relationship there? Okay. Okay, we're going to have an example 1. This circuit contains 2 resistors. I like this because it's showing a voltmeter across the first resistor, voltmeter across the second resistor, and a current meter in the middle. And you'll notice the current meter, something I really like is I want you to notice that this current meter is wired in series in the circuit. This current meter, this inline current meter is wired in series. Okay. Why is that? Oh, how about that? Get that out of here. Okay. Okay, so our example is we have a voltage drop across resistor 1 of 20 volts and a resistance of 80 ohms across number 1, and we don't know anything about the rest except that we have a 36 volt total supply. Notice down here we have 36 volt supply down here. Okay, so what does that mean to our voltage? We only have E1 and E2, so we're going to have a formula that says E total is equal to E1 plus E2, and we need to know E2, right? So if we subtract, we could get the current. That's one other way of doing it. See, the thing with problems like this is there's a lot of ways to solve this. And what Stephen here did is he found the current first so we'd have something to plug in everywhere. Because, again, current's the most important. So we want to find that first. So since we have the voltage and a resistance, we're going to divide. What's our rule? Now, don't we have a couple things in the EIR? We have voltage, that's E. We have resistance, so we can find the current. So we know the formula is E divided by R, so 20 divided by 80 gives us 0.25, right? So now once we have that 0.25 there, it's 0.25 everywhere in the circuit. So now we have at least two things over here in the totals. So we can now find our total resistance, right? One way to solve this, we get our total resistance, subtract our E1 from that. Our R1 from that. Let's see. Next step is determine the voltage drop across the resistor R2. Now we know that the voltage total is equal to E1 plus E2, so we subtract E1 from both sides, we get ET minus E1 is equal to E2, right? That's a simple enough example. And we have 36 minus 20 gives us a 16 volt voltage drop across resistor 2. So we're going to plug in our 16 volts right here. And now we can divide down, because we know E divided by I is going to give us R, right? So we're going to divide 16 by 0.25. I bet that's the next slide. And we get 64 ohms. Amazing, I tell you. And now we have figured out everything except the resistance total. Now there are two ways to do this, and I want you to remember this. Okay? In this case, he divided the voltage supplied, the voltage at resistor 2, by the current at resistor 2, which is 64 ohms. Oh, I'm sorry. I thought we had gone to the next slide. Sorry. So we know that we can find this resistance two ways. That the resistance total is R1 plus R2. So we know that we found out the resistance of R2, and we're going to add 80 plus 64, and that gives us 144. But also, I want you to notice that if you divide 36 by 0.25, do that with your calculators now, and you'll see that you come out with that same number of 144. We call that a cross-check. Actually, we call that a Mr. Rogers pure functional magic check. Is the pure functional magic still working? Yes, the PFM is still working. It's 144, so we're good to go. We know that we have gotten the right answer up here at 64 because it's true when we divide this, we get the same number. It's called a cross-check, and you need to do that whenever you see an opportunity to do it. Okay, true power, guess who added the word true here, is measured in watts. Electricity is a form of pure energy. Okay, so that's true. We don't want to get into the physics of energy, and you can't change the amount of energy, but we're converting a certain amount of energy into heat and light with an incandescent light bulb. Okay, more heat than light. And in any circuit, watts add up. At watts, power, true power, is always additive. You can always add up the true power. Is that always true of apparent power? No. It's only true when it's a purely resistive circuit and it's a purely DC circuit, because in that case, and only in that case, true power and apparent power are the same thing. Only in the case of light bulbs and DC batteries, flashlights, headlights in your car. Apparent power is true power. All the power is being turned into heat and light from a DC source. So everything adds up nice and simple. In AC, or when we have induction, that rule goes out the window. VAs don't always add up. Apparent power, which is what power you're taking in, is not always additive. So I'm going to disabuse you of that idea early on. Okay, example 4. Oops, I changed the slide. And Stevens, this is number 2. So we're going to stop for a moment. Yes, I can. We're going to stop now, and we're going to make this a very short video, because I know you can pay attention to 15 minutes. More than that, I'm not sure. So we're going to stop now.